Hello, pre-calc, and now we're on to another online lecture, this time for 12-4, derivatives on page 766. So, as is the case with a lot of our lessons that have a term in the chapter section title that we haven't talked about yet, let's define it. So a derivative of a function is the limit of the tangent line of that function. So that should sound familiar because 12-3 we did all sorts of those tangent lines of those, or the limits of those tangent lines. Remember that limit as h approaches 0 of f of x plus h minus f of x all over h. Well, the derivative, if that was just a function, the derivative would be something like this. F of x tick mark. No, I'm sorry, the tick mark would go right above, right in between, right by the end. That means f, it's like a prime symbol from those guys who remember back in geometry and move those things. That just means the derivative of the function of x. Now, one tick mark means the first derivative, two tick marks means the second derivative, etc. Now, we probably won't go into anything past the third derivative. I don't think we can go past the second derivative, but that's what that means. You do the same process over and over and over again if you really wanted to. Okay. So, when we do this, this is called a differential equation. Because we found the derivative, or we differentiated. That's what it means. The differential equation would be f prime of x, not just f of x. Okay. So, let's get into an example here. So, example 1, derivative at a point. So let's say we have something like 4x squared minus 5x plus 8, and we want to differentiate at x equals 1 or 5. Now this would be my f of x. I have to start with some sort of function. And I should, in this case, start with my tangent line, to be limit as h approaches 0 of f of x plus h minus f of x all over h. Now you may be tempted to just plug in the 1 right away for our f of x. Don't do that. Wait until we can sort of clean things up and simplify before we start plugging in values. So, remember this is f of x plus h. So everywhere there's an x, I have to plug in x plus h. So my first thing is 4 times the quantity x plus h squared minus 5x plus h plus 8. That would be my first term, my f of x plus h. And then I have a subtraction sign. And then I get my f of x, where in this case I'm plugging in x for x, so my things stay the same. 4x squared minus 5x plus 8. And I'm still all over h. Okay. Well, it's a little messy, and we still got to do some algebra things to clean up, more specifically on the f of x plus h section. So, let's do that. Well, parentheses first is the order of operations. So I need to do x plus h times x plus h, and then I have to multiply it by 4. So x times x gives us x squared, x times h gives us xh, h times x, xh, h times h, h squared. And then of course I gotta distribute my 4. So 4x squared plus x, this would be 2xh times 4, so 8xh, 4h squared. And then of course I gotta distribute my 5, so I get minus 5x minus 5h. I still have my plus 8. So I have 4x squared plus, let's see, 8xh plus 4h squared minus 5x minus 5h plus 8. And then I have my orange still of 4x squared minus 5x plus 8. Now the thing is, technically, I'm subtracting. Please do not just put the negative to the 4x squared. That's a very common mistake algebraically. So I get 4x squared minus 4x squared. So those terms are going to cross off. I get no xh's I have to take away, so I don't have to. I get negative 5x minus negative 5x. So that would be a plus, so those two cross off. And then I get 8 minus 8, so those cross off. So all I'm left with is 8xh plus 4h squared minus 5 all over h. I'm sorry, minus 5h. Now it's good because, again, like we said in 12-3, I know I did it right if I only have h's in my numerator. Now I can just cross off everywhere. So I get 4h plus 8x minus 5. I just reordered it. It's fine. Because my limit still exists as h approaches 0. So as h approaches 0, I get 4 times 0. And I don't know anything about that, so I just get 8x minus 5. This would be my derivative function. And now I can just plug in my values. So I get 8 times 1 minus 5, so let's see, 8 times 1 minus 5, which would be 3, and then I get 8 times 5 minus 5, which would be 40 minus 5, 35. Those are my values at those set points. But my derivative answer would be something like this. The derivative of this equation is 8x minus 5. Now, that was pretty messy and pretty long. These things these limits get really difficult when you have to start plugging in x plus h into multiple areas. It's not so bad when we only have to plug it in once, but here I had to distribute it, and then I had to send it over this 5 and do all these crazy things just to make it work. So, what if I told you there was an easier way? What if I told you mathematicians got tired of this, doing all this nonsense, and started structuring easier ways to work on it? Well, there is. So, I'll give you a second here to check that. Okay. So, there are easier derivative rules. And I can already hear the groans of, we did all that because there's an easier way. Yes. I encourage you guys to know where things started with in math. So we gotta help build up that backbone. And that's just algebra. That's just good for you anyway to practice. Okay. So the first derivative rule is called the power rule. The power rule says that if I have some function, if f of x equals x to the power of n, then my f prime of x equals n x to the power of n minus 1. Now it sounds really, really messy, but I promise you it works. We'll look into it in a second after we start devising all these rules. Okay. So, right into an example. Example 2. Let's use the power rule. So let's say I had some sort of function, x to the 9. We're going to do a couple of them, so just say letter A. Actually not. Well, the power rule says that my exponent gets dropped down, and then my remaining exponent gets -1. So the derivative would be 9x to the 8. And it actually holds up. So we're just going to show it with the limit way. The limit as h approaches 0 of f of x plus h minus f of x minus h, or over h, excuse me, I would get, x plus h to the power of 9 minus x to the 9. And it gets really, really messy really, really quickly. As we can already see, this is pretty gross. You would have to do like the binomial theorem and stuff like that. But what happens is I end up with x to the 9, I get 9x to the 8th h, and then I get a whole bunch of terms that are going to have h. And I'm going to have to minus x to the 9. My x to the 9s are going to cancel off, and I'm going to end up with all these terms that have h's, and as h goes to 0, the only term that's going to remain is that 9x to the 8. I probably should have done an easier example, but instead of doing all that, we can just use the power rule. Instead of having to break out Pascal's triangle to sort of do x plus h to the power of 9, mathematicians found an easier way. So, following that logic, what if I had b was square root of x to the 3rd? Okay. Now this one's a little tricky, because you want to say that the radical is just, or the power is x to the 3rd. But remember, radicals are values too. So the actual expression, this is actually x to the 3 halves. Remember, if I had something like 25 to the power of 1/2, and you type that in your calculator, you get 5. Because 1/2, or the power of 1/2, is the same thing as a square root. So essentially, I have x to the 3 times 1/2 up top, which means I have x to the 3 halves. Okay. So again, the same thing follows. 3 halves gets pushed down to the front, and I have to take 1 away from my exponent. So I get x. Now what is 3 halves minus 1? Please don't say 2 halves. Okay. It's actually 1/2. Now if you wanted to rewrite this, you could to 3 halves square root of x or something like that. But for the sake of argument, our differential equation, our power rule says that this has to be our derivative. 3 halves x to be 1/2. Now let's get one last one. What if I had 1 over x to the 8th? Okay. Again, this one's a little trickier. So I have to really recognize what this exponent is. Now this might be something you haven't seen. We haven't done a lot in pre-calc, but you should have done it in algebra. This expression is the exact same thing as x to the -8. Again, probably something you haven't seen before. If you have a negative exponent, you always just set it to the bottom. Like if I had, or back in algebra when you started working with exponents, you should have done that quite a bit. So again, I have to put my -8 out front, -8x. And now I have to take away 1 from my exponent. So -8 minus 1 is actually -9. So my power rule says that my derivative would be -8x to the power of -9. And again, if you want to write something like -8 over x to the 9 because you don't like negative exponents, that's fine. I'm not going to make it. Okay. But yeah, that's the power rule. Now, that's not the only rule of derivatives, so let's get into some other ones. That's just the most common one, and it comes up a ton. Okay. So, the derivative of a constant. So let's say if f of x was just a constant, so it was k for constant, then the derivative is 0. If there's no x term, the derivative gets washed out. It essentially becomes not a thing. Let's see, what else do we get? Okay. Sum and difference. So if I have multiple terms, so if I have like f of x equals x to the n plus x to the c plus x to the z, then my derivative, I just do each of them separately. So n x n minus 1 plus c x c minus 1 plus z x z minus 1. Sum and difference just means that I just do each term separately in a list. Just because they're being added next to each other or subtracted next to each other, it doesn't matter. Okay. And if my coefficient isn't 1, coefficient non-1, so if I have something like if f of x equals k x to the n, then my derivative just turns into, I multiply out front, so I get k times n times x to the n minus 1. My value gets bumped down, you just multiply if there's already a number there. So, for example, let's say we use the numbers we had in example 1 to follow all those rules. Well, let's say we did that. So the example 1 we had was 4x squared minus 5x plus 8. And we already did the derivative of it, remember? After doing the limit as h approaches 0 of f of x plus h minus f of x over h. We did all that stuff, we ended up with what? 8x minus 5. So let's see if the same thing happens. Okay. Well, the sum and difference rule says that I can just do each of them separately, so let's do that. The coefficient non-1 rule says that if I have to bump down this thing, but I already have a coefficient there, so I get 4 times 2, and then I get x, and then 2 minus 1, so 1's going to be my exponent, so I actually get 8x. This one's the goofy one. If x only has 1 power, it's an exponent of 1, right? So I get 1 times 5, so I get 5. Now what's x to the power of 0? Well, what's anything to the power of 0? It's just 1. So I just get 5, and of course it's a minus, so I get minus 5. And then 8, 8's a constant, so its derivative is always going to be 0. So my derivative is 8x minus 5, which is exactly what we showed with all that algebra. So these rules work. Maybe we should write that. That's fine. Just remember, so note, x to the 0 equals 1. Probably something that is going to come up quite a bit. So just remember that equals 1, because it'd be x to the 0. So yeah, that's always a fun part where I show you how to do things in a very long and complicated way, and then there's just a 10 times more efficient, easier way to do it now that we've refined mathematics. But that's the same thing for everything, right? Because honestly, what is like multiplication? Multiplication is just adding really quickly, just a whole bunch of adding, but to understand the multiplication, you have to be able to add. So all these higher level math just makes everything easier if you understand it in its cores. So let's do an example. Example 3, derivative rules. So let's say our function was something like this. F of x equals x to the 5th times 2x cubed plus 4. Well, we haven't worked with anything that has this times a quantity or some multiple quantities multiplied together. But in this case, this is pretty easy. What can I do with this x to the fifth, this term? Well, I could just distribute it. So x to the fifth times 2x to the third. Remember, if you're multiplying it like this, you would just add the exponents. So I get 2x to the eighth. X to the fifth times 4. So I get 4x to the fifth. So that's still my f of x. I haven't done my differentiation yet. Now I can. 8 gets bumped down to my 2, so I get 2 times 8. 8 minus 1, so I get 7. 5 times 4, and I lose an exponent, so 4. 2 times 8 is 16, so I get 16x to the 7. 5 times 4, I get 20x to the 4, and I still have that plus sign. So the differentiation, the derivative, would be that. Again, much easier than doing the x plus h method, because you'd have to do x plus h everywhere you see this x, you do it to the power of 8 so that many times, and that just sounds not fun. Okay. Yeah, those are derivatives. Now we're going to get into something a little different. We're going to get into something extreme. It's the extreme value theorem. Extreme value theorem. The extreme value theorem, besides being extreme, is also pretty easy to understand, and it's one of those things where you don't think we would need a written definition, but it actually matters a little bit. So let's say if a function is continuous, meaning it doesn't stop, on a closed interval, and I'm going to define the interval as bracket a comma b bracket. Remember, interval just meaning from a to b, and closed meaning those brackets, meaning we're including the endpoints. Then there must be a minimum and a maximum. Okay. That's a whole lot of fancy words for just saying if I have a function, there has to be a minimum and a maximum. So let's say if we were to graph it something like this, and I had some sort of graph who knows? But I have to define it on some interval. So let's say I had A and B. Then there has to be some minimum value, and there has to be some maximum value. Okay. And we can actually calculate these values. So to calculate these values and figure out where they are, we have to use critical points. So critical points, there's two ways to find critical points. The first one is you always test A and B. We always test our starting point and our ending point, no matter what. The other one is we have to solve f derivative of x for 0. That'll give us our other critical points. So first we have to do the derivative of our function, set it equal to 0, and sort of like factor and play that game to find these critical points. Okay, I'll give you a second there. Okay, and then I'll write on to example 5. minimum and maximum. So first we need a function. The example in the book's a big long story problem. I'm just going to say, for the sake of time, go straight to the numbers. Fx equals negative 1/3 t cubed plus 4t squared plus 11 over 3. And the interval is 1 to 12. Okay. So the first thing is we should probably just do the derivative. So f prime of x, we get 3 times 1/3, times negative 1/3, and then I get t squared. I get 2 times 4, and then I just get t, and then constant, so it's gone. 3 times negative 1/3, that would just be negative 1, so I get negative t squared. 2 times 4 gives me 8t. Okay, so now I gotta see if there's anything I can simplify and factor this down. Was there anything in both those values? Yes, there's a t, so I can factor out a t. So I get t, so I get t squared divided by t would be negative t plus 8. And then I can set each of those equal to 0, so my critical points would be t equals 0 and negative t plus 8 equals 0 plus t, so it would be t equals 8. Okay, so my critical points would be 0 and 8, and my interval would be 1 to 12. The thing is, though, 0 is 0 on my interval? No, it's not. 0 is not between 1 and 12, so it actually doesn't even matter. So all I have to check, I have to test 1, 8, and 12. I'm going to take a quick look at which equation we test those values in. I think it's our original, but I want to make sure. Yep, we plug them into our original. So I get, let's see, negative 1/3, 1 cubed, plus 4, 1 squared, plus 11 over 3. Well, let's see. Well, 1 cubed would be 1 times negative 1/3, so I get negative 1/3. I get plus 4 plus 11 over 3. So I would get 4 plus 10 over 3. Well, 10 over 3 plus 4 would be 7.333. Repeating, etc. 7 1/3. Okay. I gotta test some other ones, so let's see, 8, so I get negative 1/3, 8 cubed, plus 4 times the quantity, 8 squared, plus 11 over 3. 8 cubed times negative 1/3. Would be negative 170.6, repeating, 8 squared, 64 times 4, plus 11 thirds, so I get 430.33, or 3 repeating. So I can already tell that 7.3 repeating is naturally not going to be my maximum, but it still could be my minimum. We still have to check 12. So negative 1/3, 12 cubed, plus 4 times the quantity of 12 squared, plus 11 over 3. 12, oh shoot. LOL. This is a negative 170, I had positive 170 in my calculator. Let me fix that. So I get 256 plus 11 over 3 minus 170.6 repeating. So I should have gotten my red one 89. I apologize to those who caught that and didn't see it when I did. Okay. 12 cubed times negative 1/3 is negative 576. 12 squared times 4 is 576. And then 11 over 3, well, is just 3.6 repeating. And in this case, it actually would be 3.6 repeating. So the funny case is my minimum would be the 12. So f of 12 is my, but I got the smallest value, and f of 8 is my maximum. Okay. So that would be my answers to that one. All right, let's see. We got two more rules of derivatives to go over and two examples. I know this one was a very, very long one today. I apologize about that. Okay. The last rules we need to talk about are the product rule. So if I have f of x times a g of x, then the derivative. So another way to write derivative is d over d of x. This just means derivative. And the reason I'm going to do that is because it's a whole thing that's going on. I get f prime of x times regular g of x plus regular f of x times g prime of x. So the way I do this, I have two functions, but I multiply together. Derivative of f of x times regular g of x plus f of x times the derivative of g of x, and then I combine like terms at the end. Okay. The quotient rule. So if, remember quotient just means dividing, so I have if f of x divided by, ooh, that's a terrible g of x, then my derivative, d over d of x, would be, I'm just going to write it in here, then my derivative, differentiation in terms of x, I get f prime of x minus g prime of x, I'm sorry, f prime of x g of x minus f of x g prime of x all over gx squared. So, like I said, two examples, one doing each of them. So, example 6 is the product rule. So, I get two functions, something like x cubed minus 2x plus 7 times 3x squared minus 5. Now, technically, just like we did way back in example 3, we could actually just multiply all this stuff out and then find the derivative of that if I had one function. And some of you may elect to do that. This is just another way of solving these problems, is when you do the differentiation each separate one. So the way I do it is to keep organized. Remember, it's going to be f prime g plus f g prime. So I need all four of those. So first, my f of x is going to be my x cubed minus 2x plus 7. And then my g of x, my other function, 3x squared minus 5. Well, my f prime is just my derivative of that function. So I get 3x squared minus 2. And my g prime is just going to be the derivative of this, so I get 6x. And now I just plug things in and multiply naturally. So f prime, so 3x squared minus 2 times g, well, 3x squared minus 5, plus f, which is x cubed minus 2x plus 7, times g prime, which is 6x. Okay. 3x squared times 3x squared, that's going to be 9x to the fourth. 3x squared times negative 5 is going to be negative 15x squared. Negative 2 times 3x squared is going to be negative 6x squared. Negative 2 times negative 5 is going to be positive 10. Plus x cubed times 6x is going to be 6x to the fourth. Negative 2x times 6x is going to be minus 12x squared. And 7 times 6x is going to be plus 42x. Now, I just get in the habit of putting them in brackets. You don't have to in this case because it's a plus, but if it was a subtract, you need to do that just to keep track of terms. Okay. And now I'm just going to combine like terms. Well, I get 9x to the fourth plus 6x to the fourth, so I get 15x to the fourth. Let's see, I get negative 15x squared minus 6x squared, so negative 21x squared, minus 12x squared, so I actually get minus 33x squared. And then I get just 42x. And then I just get 10. So my derivative would be d over dx equals this. 15x to the fourth minus 33x squared plus 42x plus 10. Again, the reason for this symbol probably makes more sense now. I cannot say that this is f prime of x. I can't say it's g prime of x because it's the derivative of them being multiplied together. So that's why we have d over dx. Okay. Now on to example 7, which is the quotient rule. Okay, so I get 5x squared minus 3 all over x squared minus 6. Now, again, I'm just going to rewrite the quotient rule just so I can keep track. F prime g minus f g prime all over g squared. And then again, I'm going to find my f, my g, my f prime, my g prime just for my organizational sake. So my f would be 5x squared minus 3. In that previous example, it doesn't matter which one's f or g because they're being multiplied together. Order operations of multiplication doesn't matter, and eventually you're going to add those terms anyway. This one, order does matter. Your f has to be your top one. Has to be. And my g of x is x squared minus 6. And now my derivative, well, I get 10x for my f, and then I get 2x for my g prime. Okay. So f prime times g of x, so I get 10x times my g of x, which is x squared minus 6. And then I also get minus, and then I get g prime, f times g prime, so 5x squared minus 3 times 2x. And I'm just going to worry about the top for now. Okay, so 10x times x squared gives us 10x cubed. 10x times negative 6 gives us negative 60x. Again, brackets. 5x squared times 2x is going to be 10x cubed. Negative 3 times 2x is going to be negative 6x. In brackets, subtract. Now, see, this is where an example where keeping this matters. Because if I just had this to the 10, it would affect my 6x at the end. So, 10x cubed minus 10x cubed is going to give me 0x cubed. Negative 60x minus negative 6x is actually negative 54x. Because you subtract a negative, you're adding, and I'm going to get it all over g squared. Now the book does this, and I'm perfectly fine with it, where they just write the equation again and write a square. I'm not going to make you distribute it if the book doesn't make you either. Okay. That's the whole section. I don't know how long it is, but it felt like a long one. I hope you guys have a great day, and I hope it all made sense to you. If you have questions, feel free to let me know.